Hey everybody, so here's the video on the exercises from 3.4. The first one is going to be sketching the graph of g of x equals x minus 2x sine x on the interval 0 to 2 pi. So first things first, step one, some preliminaries. We don't really need to write it if we don't want to, but the domain is all real numbers because your function is just a polynomial piece with a trigonometric piece. Well, actually, technically speaking, so it's defined everywhere, but actually our domain is already given to us. Now that I think about it, 0 to 2 pi. Um, Now for intercepts, there's no easy x-intercept. Now you can verify this if you'd like, but the way we find x-intercepts is to set y equal to 0, the function value is equal to 0. So like the reason for it would be g of x equals 0 would imply that x minus 2 sine of x is equal to 0, and that is not an easy equation to solve. Uh, if this was 1 minus 2 sine x, that would be solvable. That's approachable, or maybe square root 3 or square root 2. Any of those things are fine, but the fact that it's got a variable here makes it a lot harder. So there's no easy x-intercept, but y-intercepts are always nice and neat to find. Y-intercept, you just set the opposite variable, so x equal to 0. That is to find g of 0, which would be 0 minus 2 sine of 0, which would be equal to 0. So the y-intercept is 0 comma 0. It turns out that it's an x-intercept and you could guess it from this, but there's no easy way to directly solve this thing. You can guess for correct answers, but much harder than it looks. Um, so with that in mind, let's see here, we've got that. And 0 is in our interval because it goes from 0, x values are from 0 to 2 pi. And last but not least, there's no asymptotes because there's no division by 0 or anything like that. So we don't really need to worry about that. So now we're on to step 2, which is finding the intervals of increase and decrease along with relative extrema. In order to do that, we need the first derivative. So g prime of x is equal to 1 minus 2 cosine of x. And so in order to find the critical values, we need to set g prime equal to 0 slash dne, where it equals 0 or does not exist. There's no places where it doesn't exist. It exists everywhere. So we don't need to worry about that. But regardless, we do it the same way. 1 minus 2 cosine of x equals 0. That gives us that cosine of x should equal negative 1 over negative 2, so 1/2. So we're trying to find x values between 0 and 2 pi. So we're trying to find angles such that cosine of x is equal to 1/2. And so we need to brush up on our trig if we don't know it already. So x should be equal to, we want the short angle. We want our triangles to look like this, right? Because we want the small side on the adjacent side. So that would be a pi over 3 for a 60-degree angle. And then from all students take calculus, that means that the second one would be in the bottom quadrant. So just in case you don't know how to do it, this reference angle is pi over 3. So the actual angle would be 2 pi minus pi over 3, which is 6, so 5 pi over 3, because this would be 6 pi over 3. This is just work that I'm thinking in my head and showing it to you on paper. So I'm going to erase this now. So 5 pi over 3 is the other option. So now that we've got those, let's do a sign chart to find intervals of increase and decrease. And we're only working on the interval from 0 to 2 pi. So g prime up top, and we've got pi over 3, and let's duplicate that and do it right there, and 5 pi over 3. And visualizing a unit circle can really help here to figure out where everything is. So 0, pi over 2, pi, 3 pi over 2, and then 2 pi to figure out what are some good guesses. Now, once again, as we've talked about in class, you could always just pick random values for x, like pi over 3 is roughly 1-ish. So you could choose like x equals 0.5, but I'd rather actually use trig values because this is a purely trig equation. So it's going to be not too terrible to plug them in. So a number that's less than pi over 3, I'd say pi over 6 or maybe pi over 2, whichever one you want. I'll choose pi over 2, but it doesn't matter. Or sorry, not pi over 2, pi over 4. And then, so once again, this is this is pi over 6, or so that pi over 3, and then pi over 5, or 5 pi over 3 is down here. So for the middle section, we've got this whole thing. So let's use pi. X equals pi. And then for this one, x equals, I'd say, 7 pi over 4. But once again, as per usual, you can definitely just use guessing numbers like 5, 6, 7, whatever it may be. You can use those if you don't want to actually pick trig values. So I really recommend it because it helps you with your trig here too. But so plug in pi over 4. That's going to be cosine of cosine of pi over 4 is square root 2 over 2. So this is really going to be 1 minus square root 2, but you can plug it in and you'll find that it is negative there. So the function is decreasing in there. And then we'll plug in pi. Cosine of pi is -1. So this will be a negative negative. So it's a positive. So it's going to be increasing here. But you can always plug it into your calculator. And last but not least, if you plug in 7 pi over 4, you'll find that it's also decreasing here. So we have a relative min, uh, right here and a relative max at 5 pi over 3. And since we're going to be sketching this function, we need to know the locations. So as a relative max at x equals 5 pi over 3. So that means that g of 5 pi over 3, if you plug that in, this is where you're definitely going to need your calculator because this is going to be a pretty nasty number when you plug it in. So it's going to be 5 pi over 3 minus 2 sine of 5 pi over 3, which if you want to try and reduce it and make it look like an exact number, that'd be fine. But since we're graphing it, I really want to know what the actual value is. And it ends up being roughly 6.97. And there's a relative min at x equals pi over 3. And then that means that well, let me actually move this down a little bit so that I can write the point right below. So this is the point 5 pi over 3, comma 6.97. Once you see my graph, you'll understand why I'm doing this. Just leaving the x coordinate as 5 pi over 3 instead of writing its approximation. But you'll see in a second. I'll explain why. So then this would be g of pi over 3, which would be pi over 3 minus 2 sine pi over 3. And that will be approximately negative 0.68. So we've got the point pi over 3 commas negative 0.68. That was step 2. We're going to put the curve, the graph down here, so just leave that space free. And then step 3. Now that we found the relative extrema along with the increasing and decreasing, we could write it out, but why give ourselves carpal tunnel? I kind of decided against it. Think about it now. So step 3 is concavity, which is the second derivative. So we're going to do g double prime of x, which would be negative 2 sine x. So just positive 2 sine x. And finding where the second derivative equals 0 or does not exist. Granted, it doesn't, it exists everywhere, so that the D&E is not useful. But regardless, you're setting 2 sine of x equal to 0, and we're asking ourselves, where does sine equal 0? Well, that would be 0, pi, and 2 pi. But those values, the 0 and the 2 pi aren't really, they're at the very, very ends of where we're working. We're working on the intervals 0 to 2 pi, so we don't even really need to write them on our sign chart. So we'll write a sign chart, 0, 2 pi, and then right dead in the center, or as center as we can be, pi. And then g double prime up top, x down bottom. Let's just pick x equals pi over 2 and x equals 3 pi over 2. But once again, you can pick whatever you want. You could pick 1 over here because this is roughly 3.14 and put 4 over here because this is 6.28-ish. So either way, if you plug in pi over 2, sign is positive. So it's going to be a plus sign here, which means it's concave up. And then plug in 3 pi over 2, sign will be negative. So it's a negative 1 over here. Oh, no. And we're concave down and we've got a frown. So that means that we have an inflection point at x equals pi. So we want to know the actual location. So we'll plug in g of pi, which would be pi minus sine of pi, which ends up just being pi, or approximately 3.14. So pi comma 3.14. And I will explain why I'm going to keep the x coordinate there in just a moment. But that gives us basically everything we need to know. Uh, so with that in mind, we're going to draw our nice little graph. And if this was a question on an exam, I would give you the right style of graph. For this one, we're really only going to need mostly just the first quadrant and a little bit of the fourth quadrant. So this one will look like this. This is how I would draw it. So draw like that. Because we're working, and the reason why I know this is I'm working on the interval from 0 to 2 pi. So I just have to stop at 2 pi. I don't need to draw any further, and I have to start my x values at 0, so there's no reason to draw the left half of the graph. Now I know I'm going to go below the x-axis for a little bit, so that's why I drew a little bit here. And so the reason why I've been leaving my x coordinates in this format is because it'll make a very, very nice way to separate the grid very nicely. So here's pi, right, in between. Instead of trying to like all of these ones are going to be, instead of trying to line up an x value, like an approximated x value and an approximated y value, why not just keep the x values here nice and neat and then approximate the y value? So I'm only having to like roughly draw one thing. That was at least my thought. So then I can split up the pi's into individual pi over 3's. So this will be pi over 3, 2 pi over 3, 3 pi over 3, which is pi, then 4 pi over 3, and then 5 pi over 3. And I see that my relative maximum is 6.97. So I'm going to make this graph go all the way up to 7. Well, I'm probably going to make 8 tick marks. 1, 2, 3, 4, 5, 6, 7, 8. And then roughly just 2 down on bottom because my relative minimum was a negative 0.68. So then I'll draw my sign charts down below, which I'm actually just going to duplicate this thing and put it right below it. Duplicate. And since I'm running out of space, I made that mistake. So let's just move this up a little bit and over. All right. And then G prime, G double prime. G prime had pi over 3 and 5 pi over 3. G double prime just had pi. And so we'll break up our interval based on those numbers. And then we should also probably just write 0. Oh, wrong stop font. 0 and 2 pi. Just to remind ourselves that we're working on that closed interval. So it was concave up and then concave down. So plus here and concave up, minus here, concave down. And then it was decreasing, increasing here, and then decreasing here. So in the interest of time, I would recommend that you pause the video and fill out this little cheat sheet that we use. But I'm going to go ahead and fill it in. It should go like this, 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 and then this. And now we'll plot all of our points that we found. We found the point 0, 0. We found the point pi over 3 comma negative 6.8. So roughly there. I mean, it doesn't have to be perfect. And then pi comma pi. So pi comma 3.14, which is roughly there. Does not need to be perfect. And then 5 pi over 3 and 6.97. So 1, 2, 3. 6, 7. So right below that line, which is right about there. So let's plot that. And then what we know based on our curve shape, it should look like this, where it's concave up until just about there, and then it starts becoming concave down. And if we really wanted to, we could plug in the endpoint as well, but it's somewhere there. It ends up being actually, what's it called? 6.28 if you want to know, but that's right about there. And that's that question. Now we'll move on to the next one, which had to do with slant or oblique asymptotes. Some books call them slant asymptotes. Others call it oblique. In a rational function, if the degree of the numerator is exactly one more than the degree of the denominator, so like numerator is the second power, denominator is the first power, that's one more, or maybe the third power and the second, or the 10th and the ninth, and so on and so forth, then you have a slant asymptote, and this asymptote is found by doing long division. The resulting quotient is an equation that for the slant asymptote. So for example, consider this function. I'm going to go ahead and find that slant asymptote for you. So you can either do long division or you can do synthetic. I'll do both here. You can skip through it if you don't want to, if you know one or the other. The only reason why I can do synthetic is because my denominator is of the form x minus a number or x plus a number. If it was 2x plus or 2x, so let's just say 3x minus 2 for a second, then I could not use synthetic. Synthetic only works when you have a denominator of the form x minus plus or minus c. So I'm going to do that though on the side. So for synthetic addition or synthetic division, you'd write 2 and then this thing. So 3, 0, 1. And then we bring down the 3. 3 times 6, 3 times 2 is 6. 6 plus 0 is 6. 2 is 18. Oh, minus 1's there, and 17. So regardless of how you do it, you're going to get the function, the quotient will be y equals 3x plus 6. Or like your quotient is 3x plus 6, so the equation of the slant asymptote will be y equals 3x plus 6. And so you could do it here as well. So you could do x minus 2 divided into 3x squared. And then I always like to have a placeholder for my non-existent degree terms. Minus 1. How many times does x go into 3x squared? It goes into it 3x times 3x squared minus 6x. Subtract it. It cancels, and we get positive 6x. Then we bring down the negative 1. How many times does 6x go into to x, or x go into 6x? It goes into it positive 6 times. 6x minus 12. And I'm getting something different, which is weird to me. So I should get, oh, that shouldn't be 18. That should be 12. I'm sorry. And so it should be 13, not 7, or it should be 11, not 17. Dope. It ends up not mattering for us. Good news. And so you get subtraction here. And these cancel, and you just left with that positive 11. So the slant asymptote is at y equals 3x plus 6 from your quotient. Now, if you want to know why you get a slant asymptote from a calculus perspective, I will add that at the end of the video. It's not required to understand if you don't want to. I would hope that your interest is piqued as to, like, because now we can finally explain that. In Math 180, 126, we could kind of give a hand-wavy reason why it works, but now we can actually explain it with calculus. So if you want to watch it, stick around for the rest of it, like for the very end. Otherwise, you can just stick around for this last problem. So for this one right here, we're going to sketch the graph of this function, y equals x squared minus 2x plus 5 over x minus 1. So we're going to start with step 1. So the domain, if you really want to write it, but it kind of just pops up naturally, is negative infinity to 1, union 1 to positive infinity, simply because we cannot have the denominator equaling 0. That's the only issue, is when x is equal to 1. So that's why the domain is that. Then we'll move on to intercepts. So x-intercepts, we try and set y equal to 0. That means saying x squared minus 2x plus 5 over x minus 1 equal to 0. And that will only equal 0 if x squared minus 2x plus 5 equals 0, but you'll find out like you can't factor it. So you would might like, so if you can't factor it, you can try and use the quadratic formula, but you'll find out there's no real zeros from quad formula. Um, and it's only complex numbers, so there's no way to get through that. And then y-intercept, we just need to find y of 0, which would be 0 minus 2 times 0 plus 5 over 0 minus 1, which ends up being just -5. So we don't have any x-intercepts. We do have a y-intercept at 0, -5. Last but not least is to have a look at our asymptotes. So we have a VA at x equals 1 from the denominator, setting the denominator equal to 0. And then because the degree of the numerator is 1 more than the degree of the denominator, we're going to have a slant asymptote. So a slant asymptote at, we're going to do the work. We're going to do long division. So x minus 1 divided into x squared minus 2x plus 5. Now, granted, you can also use synthetic division because the denominator is of the form x minus 1 or x minus c. But I'm just going to do it this way since this is more applicable to any situation. How many times does x squared or x go into x squared? It goes into it x times. That's x squared minus x. Subtract, and you get negative 2x minus a negative x. That's a negative x net. And then bring down the plus 5. How many times does x go into negative x? It goes into it -1 times. Then we get negative x plus 1, which we subtract, canceling that, and you get 5 minus 1. That'll be 4. But regardless, the slant asymptote is at y equals x minus 1. Continuing onwards, we now have to find step two, which is increasing, decreasing. So y prime is going to equal, by the quotient rule, it'll be 2x minus 2 times x minus 1 minus 1 times x squared minus 2x plus 5, all divided by x minus 1 squared. And then just foiling that out. To save on space, I trust you guys to do the algebra, but just to save on time so you're not spending all that time on it, this becomes x squared minus 2x minus 3 divided by x minus 1 squared. And that factors to x minus 3 times x plus 1 over x minus 1 quantity squared. So setting y prime equal to 0 / dne will give us 3, -1, and 1. When we plug in, we'll get the 3 from the numerator, the -1 from the numerator, setting that equal to 0, and we'll get 1 from the denominator where it does not exist. So we'll make a sign chart here. So it's -1, +1, and 3. And do so y prime up top, x down bottom, x equals -2, x equals 0, x equals 2, and x equals 4 should be sufficient. And so if you plug in negative, you should fill out the sign chart, pause it, and try and fill it out yourself. So I'm just going to actually write the answers for you. So pause it, make sure you got it right. You should get increasing, decreasing, decreasing, and then increasing. So that means you have a relative max at x equals 1, or x equals -1. And if you plug in y of -1, you will end up getting -4. So you have the point -1 comma -4, and then you have a relative min at x equals 3 and y of 3. Remember, we're plugging this into the original function. If you plug it in, you get 4. So or the point is 3 comma 4. Sorry, I had to scrunch that in. And then we go with step 3, which is to find the second derivative. Now, we talked about this before, but I want to talk about it again. You want to use the most simplified version of your derivative, of your function, to find its derivative. Since we're finding the second derivative, we're taking the derivative of the first derivative. And we could use this format, but then we'd have to do a quotient rule with a chain rule in the bottom and a product rule for the numerator, instead of just doing this one where it's just a quotient rule with a chain rule inside it. Much better. And you'll see why in a second. So f prime, so 2x minus 2 times g, which is x minus 1 squared, minus g prime, 2 times x minus 1 to the first power, technically times 1 because that's the derivative, the inside, but we're running out of space, so times g prime times f, x squared minus 2x minus 3, all divided by x minus 1, quantity squared, quantity squared. And I'll do one step of the simplification just to show you that nifty little trick. There's a common factor of x minus 1 present. So I'm going to factor that out from the get-go. So I get 2x minus 2 times x minus 1 for the first term, then minus 2 times x squared minus 2x minus 3 for the second term, all divided by x minus 1 to the fourth power, because it's going to be 2 raised to the 2. That's 2 times 2. That's to the fourth power. And then if you do go ahead and FOIL that, which I think you should do, like on some scratch paper or whatever, you will end up with, surprisingly, just 8 divided by x minus 1 cubed. So setting y double prime equal to 0 / dne, you will just get x equals 1. And so we'll make a small sign chart right down here. Doesn't need to be big because we only have one important value. Come on. 1, y double prime, x. Let's plug in x equals 0 and x equals 2. And if you plug them in, you will get, and you should test this out by yourself. The numerator will always be positive because it's just a positive 8, and the denominator should always will change sign based on what x minus 1 is. You will because it's cubed power, not squared. If it was squared, then they'd all be positive. But you end up getting concave down and then concave up. And that means that this could be a point of inflection. However, this is not a point of inflection, not an inf point, because g of 1 does not exist. The function does not exist at 1, so that is not a point of inflection, even though concavity changes. So we have everything we need. Let's make our sign chart down below. Duplicate it and stack it right on top. And then y prime, y double prime. Let's plot all the important points, which were -1 right here, 1 right here, and then it was 3, which is right there. And then, so it was positive, so it's increasing, decreasing, decreasing, increasing. And then there was just 1 for the second derivative. It was concave down here and concave up here. So we'll draw our little divider lines. And then I'd like you guys to fill in that chart. So pause the video and fill it in. What you should get is this, followed by this, followed by this, and then this. Now that we have that, we have our shape, we have a rough shape. Let's start plotting everything we know. We know we have a vertical asymptote at x equals 1. So let's draw that entire thing. Um, and then we know we have a slant asymptote at y equals x minus 1. That's a line with slope 1 and y-intercept -1. So there and there. Let's go ahead and make that dotted line. I should have made those points in purple. Not that it super matters. It's not super important, but um, that, once again, it does not need to be perfect, but it's good enough. And then we've got any points that we got. We got the point 0, comma, -5 from a y-intercept, 0, comma, -5 right there. We had -1, comma, -4 from our relative maximum, and 3, comma, 4 for our relative minimum. And so looking at the shape and remembering that we have to hug our asymptotes, this should look like this. And then kind of a similar situation for the from the top part, like that. And that is our graph. So that's how we do that one with a slant asymptote. So that'll be the end of this video. I hope these were helpful. If you wanted to know why slant asymptotes exist, like why the curve eventually looks at it, I'm going to go ahead and add an extra page here to show that. But if you're not interested, I'll see you on the next video. But otherwise, stick around. So let's look back at this example right here. Let's grab this, copy, and let's show it right down here. So we had, it was y equals 3x squared minus 1 divided by x minus 2. So um, the division algorithm, which is a theorem that we just call it an algorithm as well, what it tells you is that when you do the long division, what it's telling you is that this curve right here could be rewritten as a quotient, 3x plus 6, plus a remainder divided by its divisor. And I guarantee you, if you find a common denominator, like multiply this by x minus 2, multiply this by x minus 2, and simplify, you will get back the original function. Now, why is that important? So what that's telling us is that as x goes to infinity, positive infinity or negative infinity, it doesn't matter actually. Um, this curve on the right-hand side, this just goes to 0. Right? Because as x gets infinitely large, this will just be a finite number divided by infinity. It'll go to 0. So what that's saying is that as x goes to positive or negative infinity, your curve is looking like 3x plus 6. So this piece just doesn't matter anymore when you get to very, very large numbers. So as your x values get very, 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 very large, your function is virtually indistinguishable from this because this will just give you like 0.00000000 something. So your main values are coming, your main y values are coming from 3x plus 6. And that's true regardless of the, like, as long as it follows the rule of degree in the numerator is exactly one more, even if it would be like if it's a degree 4 divided by a degree 3, when you do the long division, you will get a linear term plus a constant divided by your degree 3 term, your divisor. Guarantee it. Do this with anything. Make this 3x to the 4th minus 1 over x cubed minus 2. I guarantee you, it'll take longer, but I guarantee you, you will get a linear term. Oh, not a constant, but a less than degree less than 3, strictly. Apologize, I misspoke. When you do this, if you make this 3x to the fourth over x cubed minus 2, you'll get a linear term plus a degree 2 polynomial, potentially degree 1 or a constant, but most likely it's going to be a degree 2 polynomial over degree 3 polynomial. And what we know from our limits at infinity is that if the numerator, like you look at the highest degree terms, this will give you a 1 over x, which will approach 0. So that's the reason why slant asymptotes exist. If you stick around, I hope you enjoyed that. Otherwise, and I'll see you on the next video.